Hi everyone, welcome back. In this video, I'm going to introduce the concept of a linked list. In order to do that, I want to start with a review of an array. The reason why is an array and a linked list are both considered to be linear data structures, meaning they store data structured in a linear one-dimensional form. Now, how arrays and how linked lists store that data in memory looks slightly different, but they can both be used to solve problems that require a linear data structure. Now, there are trade-offs to using each, and that's why I want to talk about arrays and their pros and cons, and then see how linked lists can address some of those cons, but they come, of course, with their own set of trade-offs. So let's start with an array. I have here a simple definition of an array, a sequence of contiguously allocated data elements. And the key here is contiguously allocated. This is super important, because linked lists are not going to be contiguously allocated. All of their data elements are going to be scattered throughout the heap. But arrays, their elements are not scattered. In fact, they're right next to each other. That's what makes them very fast for indexing, but very slow for growing and shrinking in size. So let's say I declare some array of integers, which I'll just call nums. Let's say there are only 3 integers in this little array. So let's fill each one of these elements to just some random numbers. So maybe the first element is 5, maybe the second element is 7, and maybe the third element is 9. And then forgive my capital letters here. These should be lower cases. But you get the point. Okay, so let's draw what this looks like in memory. So recall that nums is a pointer. It stores the memory address of the first element in the array. So there's 3 elements in this array, 5, 7, and 9. All right, so nums stores the memory address of 5, which is the first element in the array. Let's say, for example, that this memory address is 0x1000. Okay, I'm just making this up. So num stores hex 1000, the memory address of 5, the first element in the array. So when we do something like, say, nums sub 1, as I've done on the second line up here, what's really happening? Well, we can write this as pointer notation and pointer arithmetic as nums plus 1. Nums plus 1. Okay, so the compiler takes this 1 right here and breaks this down as an offset times the size, in terms of bytes, of a data element. All right, so if the offset is 1, the size of our data element is 4 bytes because each one of these elements here stores an integer, and an integer is 4 bytes. So what the compiler really does is add 4 bytes to the memory address in nums, which is hex 1000 plus 4 is hex 1004, in order to dereference and get a value at that memory address. So I'm going to head back over here and write 0x1004, because that's the memory address of 7, right? These elements are contiguously allocated, which means they're butted up right next to each other in one big block. So if each element's 4 bytes, then I know that the second element is at 4 bytes from the first element. So 1000 plus 4 is 1004. And then this third element here is going to be 1004 plus 4 bytes, which is 1008. Okay, so far, so good. Just a little bit of review. Now, let's keep kind of a little pros and cons list over here. All right, so this kind of byte arithmetic that pointers perform in order to look up an address and get a value at that address is definitely a pro, okay? So I'm gonna say big O of 1, constant time complexity for indexing, right? I can grab any element in the array and it'll take me the same amount of time regardless of how big the array is. That's the trade-off from having to allocate one big block. We have one big block, which doesn't grow and shrink in size very easily, but I can randomly access any element using constant time complexity indexing. Definitely a pro, for sure. All right, a con, on the other hand, would be big O of n. Okay, so linear time complexity, I'm gonna write growing and shrinking. So what I'm really alluding to here is adding and removing an element. If I want to have this array nums always perfectly fit for what it needs to store, then if I need to add something, I've got a multi-step process I've got to carry out. If I want to remove something, I've got a multi-step process that I need to carry out. So let me get some room over here. All right, so let's go through adding an element. Let's say we want to add 11 to the end of nums. Okay, so what I need to do is actually declare a second array, num sub 2, which is going to be 1 larger than nums. Then what I'm going to have to do is I'm going to have to copy every element from nums into nums 2. So copy, 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 and then I'm going to append 11 by putting it into the last element. Okay, so that was a big O of n, a linear time complexity algorithm, because I had to walk through each element in the array and copy it into the new array. Now I'm not quite done yet. What I need to do is I need to delete this old memory. I need to free it, right? And then I need to take nums and have it point to this new array. Okay, so this is the algorithm for adding an element to the end of an array, or adding it even to the beginning or middle. We have to make another array of size 1 bigger, copy the old values and the one new value into it, free the old memory, and then make sure that our pointer, nums, stores the memory address of the first element in the new array. If I were to go backwards, okay, say remove, what would I have to do? I would have to declare, say, nums2 again, but this time of, say, one size smaller, say only 3 elements, and then I'd have to copy over all the elements from nums that I do want to keep, minus the one I don't want to keep, delete the old memory, and then point nums to this new memory block. Okay, it's a lot of work. And that's why over on cons, I said that adding or removing an element requires big O of n growing and shrinking, because you have to do this reallocation and copy process, and it's very slow. Okay, so let's think about then linked lists. Okay, we've got a major pro, linear time complexity indexing for arrays. We've got a big con that adding or removing is a total pain and it's slow. Linked lists are going to flip these. Linked lists are going to be really fast for adding and removing an element, but they're going to be really slow for indexing. Let's see why. All right, so I'm going to start by drawing a little picture here. We're going to call this a node. Okay, and I'll write a more formal definition of a node here shortly. A node is going to be like a single data element in our array. So in our old array, we had 3 elements, 5, 7, and 9. So then I would need 3 nodes in order to store these 3 data elements. Now, what is this part over here, this kind of extra little rectangle I'm drawing? This is actually the part of the node that stores the link. What is the link? The link is a pointer that points to where the next node in the list is at in memory. Because all of these nodes are no longer going to be contiguously allocated side by side like they are for arrays. They're going to be scattered throughout the heap. This one might be at hex memory address, say 2000. This one might be at 10990. This one might be at 3AAA, something like this. They're going to be scattered all throughout. In order to keep track of where the next node, which stores the next data element, is in the list, we have to store a pointer, a link to the next node, so that we can just follow the links all over through the heap in order to find our elements in our linked list. It's actually really cool. Okay, let's take some official notes since we've seen a little bit of a picture here. All right, so what is a linked list? All right, so a linked list is a sequence, just like an array, of non-contiguously allocated, and this is the key, non-contiguously allocated linked nodes. So what is a node? A node is a struct or an object, you can use either one, that stores at least 2 member variables. And those 2 member variables are the data element, okay, so for example, an int value like we have in this example, and a pointer to the next node in the list. Now I'm going to write null if there is no next pointer or next node. So when would there be a case where a node doesn't have a valid pointer to the next node? Well, that would be when you're at the last node in the list. Next piece of terminology to learn related to linked lists is how do we keep track of the list at all? Well, we just need a pointer to the first node in the list. Just like with an array, right? If we were to go look at the nums array, nums is a pointer to the first element in the array. So we call, just by convention, the pointer that stores the first node in the array as its memory address, head. So I'm going to write head is a pointer to the first node in the list, and null if the list is empty. Just like if an array is empty, there's no memory to point to, then say nums would store null, right? It's not a valid pointer because there's no memory. So let's update our diagram then, now that we know a little bit more about linked lists. So over at the beginning, I'm going to have head. Head is going to point to this first node. Okay, the first node is at hex 2000. It stores 5. Its next pointer stores 1990. Okay, so it's going to point to the node at 1990, in which case, here I can even draw this. We can follow the node from 5 to 7. 7's next pointer stores 0x3AAA, so we can follow that pointer to get to the third node in the list, which is 9. Okay, now what should 9, this node that stores 9 as its data element, what should its next pointer point to? And the answer is null. It's the last element in the list, so it's not going to point to anything. It points to null. And we can even follow that pointer to null, which signifies that we're at the end of the list. So you can probably see how these linked list traversal algorithms are going to work, right? We start at head. While head's next pointer is not equal to null, then we can keep traversing through the list. Once the next pointer is equal to null, then we know we're at the last element in the list. The key is we're not going to advance head, because if we were to, say, advance head and have head point here, then we've lost access to the first node in the list, right? Because there's no pointer that's storing hex 2000. So we do not want to advance head through our list. None of our traversal algorithms are going to do that unless we are in fact actually updating the first node, in which case we may need to update head. So let's get rid of this. We're not going to update head. Instead, what we'll do is we will have kind of like an index I variable. I'll use blue to denote it. And like an index I variable called cur. And we'll use cur starting at head in order to advance through the list. So let's think about how we might, say, print the list. We would initialize cur to head so that they both point at this first node, node 5. Okay? We would print out the value at 5, or the value of 5, and then we would advance cur by saying cur is assigned cur next. And that would advance cur to then point to node number 7, or node that stores value 7. So now cur points here. Okay, we would check to make sure that cur isn't null. If it's not, then we would access its data value, print out 7. Then we would advance cur by saying cur is assigned curs next. Okay, so we were here. Now we're going to advance it to the node with value 9, our third node in our list. And cur, we would make sure it's not null. It's not. We would print out its value 9. And now cur would get cur next. Okay. Well, we were here. Now cur's next is null. So now cur points to null, and that's our stopping condition. Okay, we can stop when cur is null, or we can stop after we processed the node whose next pointer is null. This is always going to signify the end of our list. So let's start a pros and cons list then for linked lists. All right, so let's start with the con. Unlike arrays, we can't just randomly index to get any of our elements in our linked list. We only store head. So constant time complexity to grab head. But if we needed to go grab, say, the last element or the second to last element, we wouldn't be able to do that unless we traverse through all these blue links here in order to get to the last element or the second to last element. So because all of these nodes are scattered throughout the heap, they're dynamically allocated independently, their memory address is all over, we just store the memory address to the next node in the current node, then we can't use that cool byte arithmetic that we were using for arrays in order to index at something like, list sub 5 or something like this. Oops. List sub 5. We can't do that anymore because we can't just compute the memory address of the fifth element as an offset of the first element's address. This doesn't work. So what is one of the cons? Con is definitely big O of n for indexing. We have to walk through and count where we are in the list in order to, say, grab an element at index position 5. And that says indexing, kind of hard to read. Indexing. There we go, that's better. All right, but pros on the other hand, if I need to, say, insert at the beginning of the list, or even at the end of the list, we can make it work, or remove from the beginning of the list, or remove from the end of the list repeatedly, then I want to use a linked list over an array because it's much more efficient. So for pro, I'm going to write here, do it in orange. A pro I'm going to write here. So big O of 1, insert / removal at head. And I'm going to put here in parentheses at tail, because there are variations of linked lists where you also store a tail pointer. And if I have a tail pointer that is always pointing to the last node, then I don't have to traverse the list in order to access the last node, which means I can insert, say, at the end of the list very easily. In future videos, I'm going to go through how to do the insertion and the removal at the beginning, at the end, and randomly in the middle, and you'll see how those algorithms work. But for now, I just want to kind of give you an introduction and show you what linked lists look like and what are some pros or cons. So you can see that these pros and cons are actually flipped compared to arrays. So when thinking about your linear data structure you're going to implement for your application that maybe does, like, say, 10,000 indexes or 10,000 insertions a second, something like that, right? You're going to want to think, do I want an array that's really fast at indexing but really slow at insertion? Or do I want a linked list that's really fast at insertion but really slow at indexing? So these are trade-offs. And that's some of the beauties of thinking about different implementations of your algorithms, right? If you need some linear data structure, you're going to evaluate the efficiency of its operations in order to decide which linear data structure you want to use for your application. All right, that's it for the introduction to linked lists. In future videos, we're going to start going through some of these operations like insertion, like removal, like printing, and I'll draw pictures for those as well. So stay tuned.